Hey, welcome back to another exciting walkthrough video. This is the chi-square test of independence in R. This is a bonus video, so if you watched the previous one and you're good with it, you can go ahead and skip this one, but I want to make sure you have at least another example of seeing how this is done in R before you have to do it in the classroom, or if you just want to come back and get a refresher. So in this case, we are using the General Social Survey data 2016. I already have it loaded under the name GSS inside R here, and just as I had mentioned in the Excel version of this walkthrough video, we are using it to see if there is a difference between men and women and their opinion if women should be able to have an abortion for any reason. This gives us a null hypothesis that there is no difference between men and women and their opinion on abortion for any reason, whereas an alternative would say that there is a difference. It doesn't tell us where that difference is or how strong that difference might be, but just says that there is a difference between them. And so we are saying that the null is that these variables are independent of each other, and that the alternative says that there is a dependency, there is a relationship between them, that it does make a difference if you're a male or female, and that will help determine on what your opinion will be. So as we go through this walkthrough here, I'm going to be using a few different libraries and packages. When you get this walkthrough video script, if you need the packages, just go ahead and remove the hashtag and install the packages as you need them. But otherwise, I'm going to go ahead and load up summary tools, Desker, not to be just confused with the Desker function inside summary tools, desk tools, and PWR. Summary tools we're using just for summary statistics. Desker we're going to use for a chi-square specific crosstab. Desk tools is going to give us access to effect sizes, phi, and Kramer's V. We're only going to use phi in this video. And PWR is going to give us the power analysis for the chi-square test. First up, I always recommend that you check out your variables with a univariate descriptive statistics. Get a sense of them first. So I'm just going to do that briefly here in this walkthrough video so we know what we're talking about. On line 36, I just ran the frec command inside summary tools on gender. That tells us we have just under 2,900 individuals, and there's about 44.5% are men and about 55.5% are women. None of them are missing. I'm going to look at the Abney variable, which is abortion for any reason, and that tells us there is approximately 46% of them said yes, they would agree for abortion for any reason, and about 53.8% said no, you should not have an abortion for any reason. Note, we have just over 1,000 missing, so the most we can get when we do our bivariate analysis are only those that answered both the gender question and the abortion opinion question. So down on lines 45 and 46, I have our bivariate tables here. 45 gives just the bivariate table 2 by 2 with gender and the yes or no for your opinions, and those are the frequency counts. And on line 46, I'm adding an add margins function to the table of the two variables, and that is going to give us the the marginal sums for the rows, marginal sums for the columns, as well as the grand sum of both of them altogether. We can see that there are 1,810 individuals altogether that answered both of these questions here. Now on 48, I'm going to go ahead and save this table without the add margins. Make sure if you save it as an object, as I am doing here, you save it without the add margins. If you do, it's going to cause chaos in your chi-square because your chi-square test is going to run. It is just going to assume that the extra column and row for the sum totals are data points that it needs to use in the chi-square analysis. So just make sure you save it without the add margins if you do so. Now, on line 49, I am running the chisq.test on my object tab.abort, and I'm going to run this. Now, R is smart enough to already figure out that our results has a degree of freedom equal to 1. How is it degree of freedom 1? Number of rows minus 1 times number of columns minus 1. It's a 2 by 2 table, which leaves you 1 times 1 equals 1. R is smart enough to know that with 1 degree of freedom, it should automatically apply the Yates continuity correction, as you can see in the output results here. It says with Yates continuity correction. If you want to forcibly turn it off, or if you have a different size table and you want to forcibly turn it on, there is an option inside the chi-square.test function called correct, that if you make it true or false, it will turn on and off the Yates continuity correction. But we're not going to need to worry about that in this particular case. Now, with all good chi-square tests and many of the statistical tests that we're doing, you can save it as an object. So I'm saving my entire chi-square results, as we see here, as an object called chi.abort, and it is now stored in the memory. And just to kind of show you here, there are attributes for these. If I can do chi.abort $statistic, it will tell me my chi-square result that I just had from the chi-square test is about 0.85. I can see that the chi-square p-value is about 0.36, which again comes from the chi-square test output. We can get our observed, which are the frequencies we put into it. We can get the expected, which are the ones that we had to calculate by hand. Ours a little bit backwards. You input your observed values, you can run your chi-square test, and then you can get your expecteds, where we had to go the other way around in Excel. Now, this is nice to have these attributes because this means we can use all of them in other functions later on. So just to go ahead and interpret this before we get too far, were we statistically significant? I failed to mention that we're using an alpha of 0.05, and so our p-value of 0.36 is much larger than our p-value of 0.05. Going back to the speed limit analogy, we are speeding by a great deal over our speed limit. In this case, that means we would be in trouble with the stats police, which in our analogy means that you are not statistically significant. Your p-value is larger than your alpha, so you are not statistically significant at alpha 0.05. Therefore, we fail to reject the null hypothesis, so we have to discard the alternative in favor of the null. And the null, again, was saying that there is no difference. There's no effect. There's no difference between men and women and their opinion on abortion for any reason. We could go ahead and just stop the video at this point if all you are interested in is in the chi-square, but I'm going to go ahead and just show you how we can also look at it using a crosstab function, the effect sizes, and then we're going to go ahead and plot out our distribution curve if you'd like to do so in R. So we already activated the Desker package, but there's a function called crosstab. Just like how you would write table, there's a function called crosstab, as in cross table, specifying the same variables like we did before, but it has an option that we can turn on called CHISQ equals T for true. And if we do that and run this line, which is line 61 on my script, it is going to give us a few goodies here. So the first thing it's going to do is it's going to print out a bivariate table. And note that bivariate table looks a little bit different. That's okay. That's because it's coming from a different function than our regular table function did. But it's giving us the table with the frequencies. If you explore the crosstab function in its options, you can find other things to turn on, like you can flag on both row and column percentages at the same time with your frequencies, all sorts of good stuff. But once we turned on the chi-square equals true option, it prints for us at the bottom of the table our chi-square results right there in a single step. We didn't have to go into a table and then into the chi-square test. But this, they both have their pros and cons. Doing it through the traditional chi-square test means we can get access to the attributes of it that we can use in other functions later. And this one is just sort of like a quick and easy to get it. We don't have to worry about storing attributes for later. And we have the exact same results that we did before. Going into our effect sizes, recall that phi is the effect size for a 2x2 table, which we have here. Otherwise, we would be using Kramer's V. And in the code, I have both examples for using phi on the object, tab.abort, which is our 2x2 table. And I have the 2x2 table written out here. So I'm going to run them both back to back so you can see them on the screen, that it's going to give us the exact same results regardless of which version it is that we run. Oh, by the way, before I forget, one of the other things the crosstab is going to do, this is an option you can turn on and off from its options, is that it's also giving us a mosaic plot in this case that appears up there. So just an extra little thing that it printed out for us in one particular go. Note the mosaic plot is at its defaults. If you wanted to get a mosaic plot with customize, you'd have to run it separately and run your extra code there. But back to effect sizes. Then I want to go ahead and say, well, that is the standardized effect, 0.02 rounded. What is that on our french fry size? That is extremely small. That's like smaller than kid size small. That's almost not there at all. I'm not surprised. There's very little difference between men and women on their on their opinion of abortions. And we saw that there was no statistical difference when we looked at it with the statistical differences. But the effect size says whatever differences we're finding, it's extremely small. Let's look at it from the unstandardized version to see how that pairs up with our effect. And in this case, I am running a bivariate table, same variables as before, abony and sex. I'm wrapping that into a prop dot table with a comma 2, which is going to tell me I want column marginals. Column marginals for the proportions to sum to 1. Remember, this is saying that our independent variables in the columns, so I want the columns. If I put sex in the rows, I would be doing comma 1 to get row marginals. But then I'm also multiplying that by 100, so I can change those proportions to percentages. It's a little easier to read. And then I'm also nesting all of this into a round with a comma 1, so I can get only one decimal point after the, one value after the decimal point. Makes it a lot easier to read than having that gigantically long decimal chain. And it's going to print out for us that if we look just at the yeses for comparison, approximately 47.5% of men compared to 47.5% of men compared to about 45.2% of women agree that you should be able to have an abortion for any reason. And if we just look at this, this is about a 2.3% difference. But if you want to explore the code that I provide, I show extra little creative ways where you can make R tell you that is a 2.3% difference. But these are small enough that I just eyeballed it. Going then down into the power test. Remember, the power analysis is telling us that power itself is the probability we are going to find correct results, which means if we rejected the null, what's the chance that we correctly rejected the null? If we failed to reject the null, what's the chance that we're going to correctly fail to reject the null? So in this case, I'm going to put in the values that I have from the test so far. So pwr.chisq.test is our power analysis function. W is our effect size, and I'm just rounding this to the 0.02 is what we had before. Our N, our grand total that we had of 1,810. 1 degree of freedom. And sig level, that's our alpha, so that's 0.05. And I'm leaving power equal to null because I want to find out what's the power for this. I'm going to go ahead and run it, and it says our power, which comes out in the results there, is an abysmal 0.136 and change. It's a very low power, but keep in mind, this is also saying the power for your test, assuming all of these other characteristics that we're going to find the right amount here. So what if we said, well, what would I want to do if I wanted to go ahead and crank it up or see if I get a 0.8? So I'm going to do a variation on my power test and say, all right, let's say if the effect was large, 0.5, what would my sample size be that I would need to get it? So I'm going to make that null at the same 1 degree of freedom and an alpha 0.5, and I'm going to make the power 0.8. Remember, 0.8 or 80% is the lowest amount we're going to want in order for our research to be taken seriously. And I'm going to run that, and it's going to say, you know what, if there is actually a large effect, to detect it, you're only going to need them rounding up because we're talking about people, approximately 32 people, to find a large effect. And I'm just going to quickly go ahead in here, because I didn't have an extra line, go back and say, all right, if the real effect is 0.2, and if there is a true difference between men and women at 1 degree of freedom and alpha 0.05, and if I want to get a power 0.8, what sample size do I need then? If I run that, it says, if there really is a difference, if we should be saying that there's a difference between them at such a small size effect, we're going to need an N of about 19,623, rounding up, people. That is huge. If there truly is a difference between men and women, and that effect is going to be 0.2. Very small difference. So that's how we're going to go ahead and use the power analysis in this component. Let's go ahead and move into the chi-square plot. I'm not going to go ahead and read through what each of these particular code points are doing here, but just note that I am at first storing an object for the critical value, which is 5.991. We get that from the QCHISQ function. Then I'm also storing into X the probability, my p-value, that's 0.047. And then I'm going to go ahead and create a curve. I'm just going to run this chunk by chunk. So I'm creating the curve, and then I go ahead and run a spot that creates the red shaded region underneath the curve. And again, if any of you are interested in talking a little bit more about how this code works, come see me during office hours. We'll break some of it down. Then I'm going to run an AB line. In this case, it's going to be a blue vertical dotted line that cuts into our plot. And this is going to say this is where our chi-square value we obtained is going. And then I'm going to go ahead and run an axis function, which is going to print onto the plot our chi-square obtained value. I'm going to run another axis function, which is going to put onto the plot our chi-square critical value. And it's really crunched up down there in my plot area, so I'm going to click zoom to bring it out. And I'm going to stretch this out a little bit more so it's larger on the screen. And what we see is some number overlapping. That's just a function because we're printing onto things that are already there. But what we have is the density curve for the chi-square. Note it's got that long concave value because our degree of freedom is only equal to 1. It would bubble out at higher degrees of freedom. That red shaded region out in the tail is our critical zone. And the blue dotted line is where our chi-square value obtained is. And we wanted to have that, if we are statistically significant, that blue dotted line is going to be over in the red shaded region. It is not, so therefore we are not statistically significant. You can just sketch this out really quick with a piece of paper and a pen or a pencil, but this is a fancy way of doing it in R. So at that point, I'm going to go ahead and see you all in the next video.